Started. Good evening, everyone. It's really a pleasure to see you all here. I think some of the people came maybe from a long way. So I'd like to welcome you to the public presentation of Isabelly Rocha about her PhD. My name is Daniel Hunkeler, and I have the pleasure to represent the Dean's Office tonight. So I will first say a few words about the candidate, how her education, her thesis, and then afterwards she will give her presentation, which will be the main part, and then I will have the honor to pronounce her Doctor of Science, and we will also give the word to the PhD director, and we will also say a few words about PhD, maybe a few anecdotes, and so we'll see. And this will be the end of the official part of the presentation, and maybe there's an unofficial part afterwards. So just a few words on the parcours of Madame Rocha. She made a bachelor in computer science in the Federal University in Campina Grande in Brazil. And then she came to Europe, I think the first time for an exchange at TU Dresden, and then decided to stay there for her master thesis in computer science. And then she made another detour on the way to Neuchâtel via the TU Delft. And so she came to Neuchâtel in 2018 to start her PhD. And she defended her PhD with success on the 1st of December in the past year, with a jury of 5 members, a very international jury that evaluated the quality of the work. It was Professor Pascal Felber, that was the PhD director, Dr. Valerio Giaboni, who is the co-director, that's also in the room here, Dr. Sonia Ben-Mokhtar, the CNRS, ENSA in Lyon, France, and Professor Marcelo Pazin, of the Haute École Arc, here from Neuchâtel, and Professor André Brito from the Federal University of Campina Grande in Brazil. And so in the reports that the members of the jury wrote, I mean, they agreed all that the research is really of really high quality, very high level, and a high originality. And I just cite a few passages of the report. Maybe I do that in French because in the original, I mean, they say, I can try to translate. The research of the candidate presents really an original, undeniably an original character with a great richness of subjects that were covered on this topic of energy efficiency in computing. And the ideas that are proposed are very clearly described in the thesis and very rigorously analyzed and experimentally tested. And so the quality of the work is not only highlighted by all these reports that were very positive, but also by the fact that the work has also given rise already to 5 publications in very prestigious conferences, and I think there's more also in preparation. So with that now, we're all very glad to hear your presentation, and I give you the word.
Thank you.
Thank you for the introduction, and thank you for all of you for being here today. So I will now try to explain in very general words to you what I have done during my research, which we entitled Towards Energy Efficiency by Leveraging Heterogeneity of Clusters and Applications, which I did under supervision of Professor Pascal Felber. So I'll get started directly with some motivation. So I'm pretty sure that everyone here in the room owns at least one of such devices which you use every day to access different services, right? And some of the services, they are backed by cloud computing resources. And when you use such services, such cloud computing services, such as, for instance, let's say you upload a file to Dropbox, or you access your email, you upload some pictures to social network websites like Instagram, Facebook. What happens in the background, so at the end of the process, all this data ends up being stored in big data centers. And these data centers, they consist of tens of thousands of circuit boards, which are all racked row upon row, which, as you can imagine, then leads to a very high energy demand, which is something often overseen, right? If we just use the services directly on our devices, that's something we don't always think about what's going on in the background. So that's the first point I would like to bring your attention to. And the second is we have been observing in the last years a very rapid advance in the Internet of the Things, which means we have more and more devices and sensors producing data about different domains, right here. So you have information about machines, about devices, about facilities or vehicles, like trains, cars, and so on. So all of this data also imply in a higher demand for data storage, which then by default will also increase the demand for energy. And then the last point I want to mention in this motivation is, well, all of this data is also being used to get something useful out of it, right? So that brings us to the popularity of the machine learning applications in the past years, where we create these applications to try to extract some useful information out of all this data, which means then trying to identify patterns there or use historical data to predict something for the future. And some of these applications are illustrated here. So for instance, facial recognition, something we use when you just unlock your phone, or recommendation engines when you use sites like Netflix, Spotify, or when you're shopping at Amazon, for instance. Something also quite common is the personal assistant, and also something evolving now more, the so-called self-driving cars. And the point here is that these applications, they are backed by very complex systems, which also need very powerful machines to run. And it is still the case nowadays that many of those applications, to achieve the desired result, they need very long running times. And all of this also, again, results in a lot of energy consumption, right? So just to sum up this motivation, I think I don't need to extend myself much more, and all of you would agree with me that we are a very data-driven society, data-hungry society. We produce and consume lots of data every day, which is great, right? We are going to reaching great things in different domains. We are evolving different domains due to that. But on the other hand, there is this problem on the energy consumption of all of that is something often overseen there. So just to give a little bit of the idea of how relevant the problem is, there are several studies making this kind of projections on how much energy we are using in the communication technology domain and so on. Here I brought just one of them for you to have an idea of how the scenario looks like. So in that case, we put into perspective with the global electricity usage to kind of have a better sense of what that means. And if we look in the worst case here of that plot, we see that by 2030, this share would be corresponding to 51% of this electricity, which is quite a significant and alarming number. But even if we take the best case scenario into account, and we zoom into that, and then we look where from this utilization is coming, we see that a big chunk of this utilization is coming from data centers. And not only that, but also the trend is showing that the utilization corresponding to data centers is increasing every year more and more. So as a response to that, the major data center operator companies, they are already embracing that cause and starting to take measures, such as, for instance, starting to sign renewable contracts, right, where they say they would be using renewable energy, which is already a great step. But as we can also see in that graph, in that illustration here, there is still a lot to do in that domain specifically. And apart from that, also there are different ways that we could tackle that problem. So this is not the only direction that we can go. There are many other things that we can do to try to have more energy efficient computation. So in my work, the way I try to achieve that is by leveraging the heterogeneity that we see present in clusters and in applications, to try to then have approaches which, considering that, will lead to more energy efficient solutions. And what does that exactly mean? Well, my assumption initially is, since we have these different applications, so I assume that those applications, they also have different requirements. They have different requirements, they have different priorities, trade-offs that are valid for one and not for the other. And similarly, in the side of the clusters, we have many different hardware types available nowadays. And the general idea is, if we understand well the demand of the applications and also of the profile of these different types of hardwares, then maybe we can make this allocation of resources in a more energy efficient way, such that we reach the goal that we want to achieve. And we can do that from two different perspectives, right? We can say that, well, the guys managing this cluster, they should take care of everything. So the developers of applications, they don't need to do much. They just specify what are the kind of requirements they have and so on. And then everything would be taken care of in the cluster management side. Or we could say, well, there's also application-specific optimizations that we can do to achieve the same goal. So we put then the responsibility on the side of the application developers. So I will start from the first case. And for that, I would like you to imagine a scenario that we have illustrated here. So there is this heterogeneous cluster with different computing nodes, different types of hardware, and there is this queue of several tasks to be scheduled in that cluster. And typically what we have in between is a guy that we call a scheduler, which takes care then of exactly like mapping these requests from the tasks to the available resource in the cluster. And this can be done in several different manners, right? You can just say first come, first serve, and then when the resources are available, they get the place. But in our case, we would like the scheduler to be able to do this thing with the objective in mind of optimizing the overall energy consumption of the cluster. And for that, it would be very great if the scheduler had some characteristics, like for instance, monitoring. If the scheduler would have, let's say, eyes over the whole cluster, it would understand the kind of profile the machine has, all the resources that are available there, and so on and so forth. So it can have a big picture of everything that is happening there and have some insights on the types of hardware that you have. Then the second would be storage. So if the scheduler can also remember the decisions it had, it means then that when it receives a similar task, which it received in the past, then it would already know what kind of decision to make. So we could leverage the historical data to make future decisions in also a more efficient way. And then the last characteristic would be prediction. So if the scheduler could had the possibility of predicting what kind of performance in terms of energy or whatever other requirement it would be from the task, if the scheduler would be able to predict already what would happen in the different machines, in the different types of machines, then this decision could also be done easier, right? So once you have all this information in hand and taking care of this whole scheduling techniques becomes much simpler. And then considering this, that's exactly what we have done. One of the first works that I did was a scheduler which we called HITS, and it was capable of doing exactly those things that I described to you, and at the end we indeed observed a better performance using it. And then you might ask me, well, we have been better than what, right? We like to compare things when we're doing research, so we need to have a baseline for that. And here I don't want to go into the details of the results, but it's just to show you that we did test this prototype implementation and compared with the scheduler that was already existing on the system that we used to do it for. We observed runtime improvement of up to 15% when runtime was the focus of the scheduler, and 7% improvement on energy when the energy was the focus of that scheduler. So this is already some interesting results. But now let's imagine that we change that scenario a little bit, and instead of having only one queue, we have now several queues representing different priorities of the tasks. And also, they are all trying to compete for the same type of resource. So they have this big data engine. All of them wants to have a slot into there. And as soon as the system is saturated, so let's say there is no more free slots, a typical approach here is to evict the low priority jobs. So we say we remove the low priority jobs to give space to the high priority ones. It's a priority system, so that's the idea, right? To give the priority to the higher ranked guys. But as you can also imagine, there is also a lot of resource waste that comes together with this, since we are like doing some computation and then stopping it, and then the same computation needs to be scheduled again to repeat again. So there is this resource there that's getting wasted, and we would like to avoid that. So what we proposed then in that specific scenario was that, well, maybe instead of dropping the whole job, we could just drop parts of that job. We could just drop some of the tasks of it, so that we can finish quicker and then give place to the higher priority guys, right? And of course, there is then a drawback here, which is you would not have the same accuracy that you would have if you would run all the tasks of that job. But the idea we have is, well, if we know the tolerance threshold for that given job, and we make sure that we respect that, then it's fine, right? And it should be good to go. You're not hurting any requirement. But now, how do you make sure of that, right? So to be able that we can do that, we then designed some models, which could, first one here that I have is, well, we could predict we could measure the arrow for each kind of ratio that you design. Each dropping ratio, we could measure what is the arrow that this dropping this amount of tasks is leading to. And this is already good, but this alone wouldn't do the job, right? So we also have another defined other methods to be able to predict the response time of the job given a dropping ratio. So with these two information together, then we can work easily, because, well, as you can imagine, so now we have the threshold that is accepted from the arrow. So from that, we could understand what is the dropping ratio that we can go up to. And then there, with this, we can say, okay, dropping this amount of tasks, how much am I earning on the performance side? And, and with that view, we can then make the decisions of how much tasks to drop and from which jobs is more beneficial to drop those tasks. So you can then find the optimal scenario overall. And just to put this all together, so we had here where you have the tasks that are having the queues. We have something we call a Task Deflator, which takes care of doing all of that I just showed you, and then gives already the information necessary to the processing engine, which you also modify to be able to actually perform that kind of modification. And well, if you think about, this is a nice alternative, but it's not completely equivalent to the one I mentioned before, to this preemptive system that I mentioned before, because we are giving space to the priority jobs, the high priority jobs earlier than it would be, but still it has to wait for some time, right? And sometimes these higher priority jobs, they have very hard constraints when it comes to performance. So one last thing that we added there was this, what we call there, this printer component that can accelerate the high priority jobs in order to compensate for that waiting time. And then putting all these components, all these ideas together, we could then observe the expected results that we had. So on the results, I don't expect you to look into details on these plots. Again, it's just to show you that we have done also several experiments. This is some of them, where we compare our approach with the preemptive system that I explained at the beginning. And then here we observe up to 55% improvement on response time and up to 40% on energy efficiency. So the numbers are quite significant. So this was it for this specific approach. And with that, I also conclude then the part where everything that we explored with regard to the management of the cluster, and we moved then the view to the developers of applications, right? So here the idea is we assume that the guys developing those applications, they are the ones who know the best about what's going on there, and we expect them to be able to do if you dive deep into the application, then you can probably find ways to tweak that application to also reach the goal of being more energy efficient in that specific domain. So I'm not saying this is the case for all the applications. I'm sure it's not. But in some cases it should be possible, and to show that I pick then one specific use case application and I then export that one and try to do these optimizations on that specific application. And this use case is in the context of hyperparameter tuning. So here I brought a very typical example of image classification, where you have a bunch of photos and you want to train a network such that it can understand, for instance, in that case here, what are the pictures of cats and what are the pictures of dogs. And with the technology we have nowadays, this is pretty straightforward to do, right? You can just automatically train all the model parameters that fits in that setup. But before you start the training, there are some questions that you need to answer. There are some other parameters you need to set up, which also impact directly into the accuracy of the model and also the performance of the final model that we get. Questions such as how many layers the network should have, for instance, or how many epochs should the training be running for, how many neurons should each layer have, which learning rate to define, and so on and so forth. The list of this kind of parameters is very extensive. And these are then the so-called hyperparameters, so everything that you need to tune before you even start the training. So then the question would be, okay, so how to find the optimal set of parameters for a given workflow, right? To first understand the problem. And the idea, like very basic idea, is as simple as trial and error. So the user simply sets them, values, it trains the model, and you check the score. If you're happy, great. Otherwise, you repeat that over and over again until you reach the performance that you want to have with your model. And as you can imagine, this very quickly becomes a cumbersome process, which is not manageable manually. So that's also the reason why out there in the literature, there are already a lot of tools which automatize and try also to optimize that process. Here I listed some examples of them. We have some coming from the industry, for instance, like SageMaker or Google Bezier, but also some open source ones like Tune or Optune. And how these tools work is, as you see here, they get as input the model, the data set, the hyperparameter you're trying to tune, the set of values that each of these parameters might assume, a metric of interest and which function you're trying to optimize. And then these tools will be working as a black box, and it will give to the user already the training model and the set of optimal parameters. So now the question is, what we want to do is find these application-specific optimizations such that we also reach our goal in the specific context. So for that, we have designed and implemented one of these tools, which named PipeTune. And PipeTune had two main characteristics, which differs from the state-of-the-art ones, like the ones I just showed before. So the first one is we also focus on reducing the tuning time itself, because mainly these auto-tuners, they are completely focused just on the final model, and they forget like that we can also automatize the tuning process itself as it goes. And we do that by including in that list the system parameters, such that we can find the optimal configurations and then reduce the overall runtime there. So this is the first point. And the second point is that we also include then the energy as part of the objective. So we also do the whole tuning process, taking the energy objective into account, which is not something very common from the other existing tools. And here, again, I don't expect you to look into all those numbers. It's again just to show you we have tested our approach with several different workflows, comparing different baselines, and we could then observe up to 50% improvement on the training and tuning duration, and up to 60% improvement on the energy consumption of our approach, which is great. But now if we go back and look into the output that the user gets, we see that, well, we have the training model, we have the setup of the optimal parameters, but then if we ask the question, right, but what's next then, right? There are then many possibilities. One of them is we could say the user wants to retrain the model with different data sets, for instance. So in that specific case, the optimal set of parameters would be useful, right? Because it's not even that it will also work for a different data set, but it's something that it would be at least a starting point for the user. But actually, most of the time what happens is the users, they want to deploy the model for inference on production, right? So they have done they have a training, testing, and now let's deploy it on production to test it on the real world. So then there are other questions that come when you want to do that, right? So for instance, which type of hardware should I use to deploy my inference model, or which system configurations to request, or which batch size to define, and so on and so forth. Again, there are many questions here that are not answered by the output that we get after this whole tuning process, right? So considering that, we went back to what we have already done before in terms of hyperparameter tuning, and we tried to extend our approach to make it also more more inference aware. So what does it mean here to be inference aware? What I mean is that during this tuning process, the user is also able to take the inference into account. So if it has some objective for the inference itself, it can also be taken care directly on the tuning and training process, and at the end you would have that as a result. So one advantage is that we have more useful information for the user, because it can take everything and go deploy the model with all the information that is given. But second is also that doing it that way, we can also optimize the model such that it will be performing in a more energy efficient way also in the inference side. So we kind of close that cycle, and we then perform the optimization in both sides, both training and inference sides. And then, of course, we were then evaluating that approach. And first, we observed some further improvement on the tuning runtime and energy consumption. This was due to some further optimizations that we could include into this extended version, which I do not have time to go into the details here. But the most important was that we could indeed optimize the throughput and energy of the inference side, as it was the objective that we had. Okay, so with that, I partially closed the sides of the application, but there is just one last thing that I would like to bring your attention to. To conclude that side, here in this illustration, you might have noticed that I tried to illustrate some nodes as being like secure nodes. And I did that because that's also, there was also a small part of my work where I looked into the security perspective, and I do it then in the same context. So here the assumption is that this heterogeneity of clusters is also with respect to security. So I have some nodes that where security is given and others where it's not. And since I'm considering this heterogeneity from the hardware perspective, then we also rely on hardware-based mechanisms to achieve the security. So in this case, we were using what is called memory assistant mechanisms, like Intel SGX, for instance. But I won't go into many details here. I just would like to mention in a single slide that we did also an approach among those lines, where we consider that not only the cluster can be heterogeneous in that security sense, but also the application. So it's not that a full application needs to go into a secure node, but it's often the case that parts of that application, only parts of it are accessing user-sensitive data, for instance. And then we developed this approach where the application developer could then label what parts of the application should go into the protected nodes, and then everything, and also of course then signaling how the data dependence works between the different parts of the code, and then just all the rest would be done automatically in the background. And then just very quickly, we also then evaluated that system, and comparing against using just the secure mechanisms without any of the other optimizations that we proposed, we also observed quite significant improvement both in runtime and energy consumption. Okay, so this that concludes both parts, and I think I went very general lines and quickly through every piece of work that I did during these last years. So now just to bring everything to an end and summarize it in a very simple way. So if I had to say in one sentence what I have done during these last 4 years of research in a simple way, I think what I would say is that I worked and I tried to propose some mechanisms and approaches which try to combine the diverse requirement of applications with the heterogeneity of clusters in terms of types of hardware available to achieve energy efficiency. And then the final question would be, well, did I reach my goal? As we talked at the beginning, this is a very broad problem, right? So it's an area that has to be tackled from different perspectives to be able to reach this final objective. But I do believe that the approaches that we proposed came a little bit closer to a solution, and also most importantly, it opened the horizon and more questions to explore it from a perspective that has not been explored before. So this is all from my side. Just now, thank you.
Okay, thank you for this really nice presentation. I mean, nicely also showed that the research wasn't just on a high scientific level, as the jury member highlighted, but it also addressed really very important issues for society, how we can go into the digital age without spending too much energy on it. So
yeah,
it was really very nice. So with that, we now come to the really special moment where in the name of the Dean's Office, I have the privilege to award you the title Docteur et Sciences de la Faculté des Sciences de l'Université de Neuchâtel.